There is a word that scientists use carefully: pattern, not coincidence, not anomaly, not isolated event. Pattern, because a pattern implies something repeating, something happening more than once, something that, once you have seen it enough times, stops being surprising and starts being the way things are. In October 2017, a telescope in Hawaii detected something moving through our solar system that had not come from within it. An object on a hyperbolic trajectory, moving too fast at the wrong angle, from the wrong direction, to have originated anywhere near our sun. They named it Oumuamua. They studied it for weeks before it disappeared back into the dark. And when it was gone, the scientific community sat with something that felt, in the most precise sense of the word, unprecedented. The first interstellar object ever detected passing through our solar system. The first. That word carries an implication that nobody said out loud immediately, but that everybody understood. First implies the possibility of second. First implies that whatever produced this object, whatever process sends material drifting between stars across the light years of empty space, might not be a singular event, might not be a cosmic accident too rare to repeat in any human lifetime, might be something the galaxy does routinely, and that we had simply never had instruments sensitive enough to notice before. 2 years later, in August 2019, an amateur astronomer named Gennady Borisov found a comet in the night sky. It had a tail, it had a coma. It looked, at first glance, like thousands of comets that had been catalogued before it. And then the trajectory came back from the calculations and the word appeared again: hyperbolic. The second interstellar object, 2I/Borisov, different from Oumuamua in almost every physical respect. A comet where Oumuamua had been something stranger, icy and gassy, where Oumuamua had been dark and dry, behaving according to known. Physics, where Oumuamua had persistently refused to, but identical in the one characteristic that mattered most: it had not come from here. At that point, 2 detections in 2 years, the word pattern began to be used more carefully, cautiously, with the restraint that scientists apply to conclusions they want to make sure they have earned. 2 data points are not a pattern. 2 data points are a coincidence that might become a pattern if a third arrives, and might remain a coincidence if it does not. The third arrived. In the spring of 2025, the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to give Earth early warning of objects that might be on a collision course with our planet, detected something new moving across the sky. The initial data was filed and flagged and passed to the people whose job it is to calculate where things in the solar system have come from and where they are going. The trajectory calculation came back. And for the third time in less than a decade, the result was the same. This object had not come from our solar system. They designated it 3I/Atlas, the third interstellar object, named as the naming convention demands, with the prefix that marks it as something that arrived from somewhere else, from the space between the stars, from a journey of unimaginable duration across the cold dark that separates one solar system from the next. And this time, when the scientific community received the news, the response was different from what it had been in 2017. In 2017, there was astonishment, the genuine, wide-eyed disbelief of people who had theorized that interstellar objects might exist, but had never expected to actually see one. There were press conferences and papers and a scramble to point every available telescope at the sky before the object disappeared. The reaction was the reaction of people encountering something genuinely unprecedented. In 2025, there was still astonishment. But underneath it, something else, something quieter and in some ways more significant recognition. Because 3 detections in 8 years is not a coincidence. 3 detections in 8 years, with improving instruments and expanding survey coverage, is the beginning of a data set. It is the universe presenting its credentials, showing us, patiently and repeatedly, that the space between stars is not as empty as it looks. That material moves between solar systems. That the galaxy exchanges matter with itself on timescales so vast that we had simply never been looking long enough or carefully enough to notice. If this is the kind of content you want more of, subscribing to The Cosmic Depth takes 2 seconds, and we post new documentaries every few days. Because what 3i/Atlas represents is not simply a third entry in a list of unusual astronomical detections. It represents a shift. The shift from treating interstellar objects as extraordinary exceptions to the rules of our solar system to understanding them as ordinary participants in the life of the galaxy. The shift from wondering whether the space between stars contains anything to beginning to catalog what it contains and why. The shift from a universe in which our solar system is an island, isolated, self contained, separated from everything else by distances so vast as to make contact essentially impossible, to a universe in which something is always moving between the islands. Something has always been moving between the islands. We simply did not know how to look until now. 3i/Atlas is the third visitor. It will not be the last, and the questions it raises about where it came from, what it is made of, how long it has been traveling, and what its arrival alongside Oumuamua and Borisov tells us about the structure and behavior of the galaxy we live in, are questions that astronomy is only now developing the tools to answer properly. We are going to follow those questions all the way down, starting with what 3i/Atlas actually is. The first thing you notice about 3i/Atlas when you look at the data is how fast it is moving. Not fast in the casual sense that people use the word for things that impress them. Fast in the sense that matters in orbital mechanics. Fast relative to the sun, fast relative to our solar system's own motion through the galaxy. Fast in a way that tells you immediately and unambiguously that whatever produced this object and sent it in this direction did not do so recently and did not do so nearby. 3i/Atlas entered the observable range of our telescopes, moving at approximately 67 kilometers per second relative to the sun. 67 kilometers every second. To put that in terms that mean something, the Earth orbits the sun at roughly 30 kilometers per second. Our planet is moving through space right now at a speed that would take you from one side of a large city to the other in a fraction of a heartbeat. And 3i/Atlas arrived moving at more than twice that speed. More than twice the velocity of a planet in a stable orbit around a star. Moving with the momentum of something that has not been gravitationally bound to anything for a very long time. Moving with the freedom of an object that belongs to no star system, that drifts through the interstellar medium answerable to nothing but its own inertia and the faint, distributed gravitational pull of the galaxy as a whole. That velocity is itself a form of information. Objects that originate within our solar system Comets, asteroids, the various chunks of rock and ice that inhabit the spaces between planets, move at speeds consistent with being gravitationally bound to the sun. They are, in the most literal sense, falling, falling toward the sun or falling away from it, but always within the sun's gravitational grasp, always moving at speeds that reflect their relationship with a central mass they cannot escape. 3. I/Atlas is not falling. It is passing through, and its speed tells you that it has been passing through interstellar space for long enough that the sun's gravity is simply an inconvenience it will curve slightly around before resuming its journey in a direction that has nothing to do with where it came from. The trajectory calculations placed its closest approach to the sun, its perihelion, inside the orbit of Mars, close enough to be warmed significantly by solar radiation, close enough for any volatile materials on its surface to begin sublimating, close enough for instruments on Earth and in space to gather the kind of detailed spectroscopic data that reveals what something is made of at a chemical level. This is where 3I/Atlas begins to tell a more complicated story. Because when astronomers pointed their instruments at it and analyzed the light reflecting from its surface and the gases streaming from it as solar heat did its work, what they found was a mixture of the familiar and the unexpected, a chemical profile that in some respects resembled known cometary material and in other respects showed signatures that required more explanation than the simple label comet was able to provide. It had a coma. Unlike Oumuamua, which showed no signs of outgassing and no coma at any point during its passage through the inner solar system, 3I/Atlas developed a visible coma as it approached the sun. A cloud of gas and dust surrounding the nucleus, glowing faintly with reflected sunlight, streaming away in the direction opposite the sun to form the beginnings of a tail. In this respect, it resembled Borisov, the second interstellar object, more than it resembled Oumuamua. It was behaving in the most basic observable way like a comet. But comets in our solar system have a reasonably well understood chemical composition. They are relics of the early solar system, frozen records of the chemistry present when the sun and its planets were forming, preserved in the cold outer reaches of the solar system for billions of years, and only released into the inner system when gravitational perturbations send them falling toward the sun. The spectroscopic signature of 3I/Atlas was consistent with some of that chemistry and inconsistent with other parts of it in ways that suggested its formation environment had been different from our own solar system in specific and interesting ways. The ratios of certain isotopes, the relative abundances of different forms of the same elements, which are set by the conditions present when material forms and do not change significantly thereafter, pointed to a formation environment with a different chemical history from our own. Not dramatically different, not alien in any science fiction sense, but different in the precise, measurable way that tells a geochemist or an astrochemist that the rock or ice in front of them came from somewhere specific, and that somewhere is not here. This is one of the most remarkable things about 3I/Atlas and about interstellar objects in general. They carry the chemistry of their home systems inside them. A comet from our solar system is a chemical record of the conditions present around our sun 4.5 billion years ago. A comet from another solar system is a chemical record of the conditions present around a different star at a different time in a different part of the galaxy. When 3I/Atlas passed through the inner solar system and released its gases under solar heating, it was, in a sense, exhaling the atmosphere of another world, releasing molecules that had been locked in ice since before our solar system existed, carrying the chemical fingerprint of a star we may or may not have catalogued, in a system we may never directly observe. The size of 3I/Atlas is estimated from its brightness and the assumptions that can be made about its surface reflectivity. These estimates carry significant uncertainty. The reflectivity of an interstellar object's surface is genuinely unknown because we have no direct reference point for objects that have spent millions or billions of years in interstellar space, exposed to cosmic radiation without the protection of a nearby star's magnetic field, accumulating surface alterations that no object in our solar system has experienced to the same degree. The best current estimates suggest a nucleus somewhere between 1 and 10 kilometers across, large enough to have survived the stresses of interstellar travel intact, large enough to produce a substantial coma and tail as it heats up, small enough to have been ejected from its home system by gravitational dynamics without requiring any particularly exceptional event to have caused the ejection. The shape is harder to determine. Oumuamua's shape was inferred from the dramatic variations in its brightness as it rotated, variations so extreme that they implied an object vastly more elongated than anything previously observed in our solar system. 3. I/Atlas, by contrast, shows brightness, variations that are significant but less extreme, suggesting a shape that may be irregular, perhaps somewhat elongated, but not in the almost impossible proportions that made Oumuamua so difficult to explain through natural formation processes alone. In this, as in its coma and its general cometary behavior, 3I/Atlas sits somewhere between the two objects that preceded it. Less strange than Oumuamua, more exotic than Borisov, not neatly categorizable as any single known type of solar system body, but recognizably related to things we have seen before in ways that make it possible, this time, to ask more precise questions than the ones Oumuamua left us struggling to formulate. And the most precise question, the one that all the trajectory data and all the spectroscopic analysis and all the brightness measurements are ultimately building toward, is not what 3I/Atlas is made of, or how big it is, or what shape it happens to be. It is where it came from. That question has an answer, a partial one, an imprecise one that carries the uncertainty inherent in tracing a trajectory backward through millions of years of galactic motion, through a galaxy where everything is moving and nothing holds still long enough to provide a fixed reference point. But an answer nonetheless. And the answer points in a direction that changes how you think about the object currently moving through our solar system and the journey it has made to get here. To understand what 3I/Atlas means, you have to go back to the beginning, not the beginning of the story of interstellar objects, because that story is as old as the galaxy itself, full of objects that have been drifting between stars for billions of years before any human being existed to notice them. But the beginning of our awareness of that story, the moment when we first looked up with instruments precise enough to see what had always been there and finally recognized it for what it was. That moment was October 2017, and the object at the center of it was Oumuamua. We covered Oumuamua in full in a previous documentary on this channel. The complete story of its discovery, its strange shape, its impossible acceleration, the Harvard professor who suggested it might be artificial, and the 45 years of silence that the wow signal left behind for context. If you have not seen it, the link is in the description. It is the foundation of everything that follows here. But the essential points are these. Oumuamua arrived from the direction of the constellation Lyra, moving at a speed that made its interstellar origin immediately obvious to anyone who ran the trajectory calculations. It had a shape, dramatically, almost impossibly elongated, with a length-to-width ratio estimated at somewhere between 5 and 10 to 1, that no known natural process in any solar system was understood to produce. It showed no signs of outgassing as it was heated by the sun, no coma, no tail, nothing that would identify it as a comet in any conventional sense. And then it accelerated. Not in the way that gravity predicts, not in the way that solar radiation pressure could fully account for given its estimated mass and dimensions. It moved faster than it should have, departing our solar system with an extra push that the best natural explanations struggled to explain cleanly, and that the least natural explanation, an artificial light sail, pushed by the suns, radiation fit the data with an uncomfortable precision. We never resolved what Oumuamua was. It departed before we gathered enough data. It is now in the dark of interstellar space, billions of kilometers from the nearest star, irretrievably beyond the reach of any instrument we currently possess or could reasonably build in the coming decades. Whatever secrets it carried, it took with it. And then, in August 2019, Gennady Borisov changed the conversation. Borisov was an amateur astronomer working from a private observatory in Crimea, not a professional scientist, not a funded research program, not a government telescope array. A person with a telescope and the patience to look carefully at the sky, night after night, cataloging what he found. And what he found on the 30th of August, 2019, was a faint smear of light with the unmistakable profile of a comet. A nucleus surrounded by a diffuse coma, already beginning to develop a tail as solar heating worked on its icy surface. The trajectory calculation came back hyperbolic. 2I/Borisov, the second interstellar object, and Borisov was, in almost every respect that Oumuamua had been strange, ordinary. It had a coma, it had a tail, it outgassed visibly and predictably as it approached the sun. Spectroscopic analysis revealed water ice, carbon monoxide, and a suite of organic molecules, the standard chemical vocabulary of comets within our own solar system, present in proportions that were not dramatically different from what you would find in a comet that had formed around our own sun 4.5 billion years ago. Borisov was a comet from another solar system, yes. A visitor from the interstellar dark, carrying the chemical record of a system we had never seen, but structurally, behaviorally, chemically, a comet. It followed the rules. It did what comets do. This was both reassuring and revealing. Reassuring because it suggested that the basic chemistry of cometary, bodies, the ices, the volatiles, the organic compounds, appears to be universal. What forms around our sun also forms around other stars. The building blocks of our solar system are not unique to us. They are the default output of the planet formation process across the galaxy, suggesting that the raw materials of chemistry and potentially of life are present wherever stars burn and planets coalesce. Revealing because it made Oumuamua look even stranger by comparison. Borisov gave scientists something they had not had before: a baseline, a reference point. an example of what an interstellar object looks like when it is behaving naturally and following known physics. And when you place Borisov's behavior beside Oumuamua's, the differences are not subtle. They are stark. Borisov is everything a natural interstellar comet should be. Oumuamua is almost nothing that a natural interstellar object should be. The contrast sharpens the question that Oumuamua first raised, without answering it. Two interstellar objects, one that fits perfectly into every known category of solar system body, one that fits into none of them. What does that tell us about the population of objects drifting between stars across the galaxy? It tells us that the population is diverse. It tells us that the interstellar medium, the vast, cold, mostly empty space between solar systems, contains objects of radically different types. Some of them are comets, recognizable and understood, carrying familiar chemistry from unfamiliar places. Some of them are things we do not yet have adequate categories for. Things that were produced by processes we do not yet fully understand, under conditions we have not yet mapped, in environments that the limited sample of our own solar system has not prepared us to recognize. And now there is a third. 3I/Atlas sits between its two predecessors in ways that are scientifically useful and philosophically interesting. It has a coma like Borisov, behaving in that fundamental respect like a comet. But its chemical signature carries the kind of specificity that points to a formation environment distinct from our own, in the way that Oumuamua's properties pointed to something that did not quite fit any known formation model. It is not as strange as Oumuamua. It is not as straightforward as Borisov. It occupies a middle position that suggests the population of interstellar objects is not neatly divided into two types, the normal and the inexplicable, but exists on a spectrum. A spectrum of compositions, shapes, behaviors, and origins that reflects the genuine diversity of the hundreds of billions of solar systems that have formed, evolved, and in many cases ended throughout the history of the Milky Way. Each of the three objects we have detected is a sample from that population. Each is a fragment of a solar system we will never directly observe, a piece of a history we cannot access through any other means, that has been delivered to our doorstep by the physics of orbital dynamics and the patience of geological time. Oumuamua was the discovery, the moment of realization that the interstellar medium is not empty of solid objects, the first fragment of another solar system to fall within our instrument's range. Borisov was the confirmation, the proof that what Oumuamua represented was not a singular anomaly, but the first detected instance of a phenomenon that the galaxy produces routinely. The ejection of cometary material from solar systems into the interstellar medium, where it drifts for millions or billions of years before encountering another star. 3I/Atlas is something more than either. It is the beginning of a pattern becoming visible. 3 objects, 8 years, each one detected because our instruments have been improving, because the surveys scanning the sky have become more sensitive, more comprehensive, more capable of catching fast-moving, faint objects before they slip past unnoticed, each one teaching us something that the previous ones could not teach alone. And what all three together are beginning to teach us, slowly, incompletely, with the inevitable uncertainty of a science that is working from a sample size that is still very small, is something that changes how you think about the solar system you live in. Not as an island, not as an isolated pocket of matter gravitationally bound to one star, separated from everything else by the impossible emptiness of interstellar space, unreachable and unreaching. But as a node, a point in a vast, slow, continuous exchange of material that has been happening across the galaxy for billions of years. A system that has received visitors from other systems and has sent its own material outward into the dark, where it drifts toward other stars that we will never visit, carrying with it the chemistry of our own formation, the chemical record of our sun, our planets, our particular corner of the galaxy, to be discovered perhaps by instruments we cannot imagine, operated by minds we have never conceived of. The question of where 3I/Atlas specifically came from, which star system ejected it, how long ago, and what that journey through the interstellar dark has done to it, is one that the trajectory data is beginning to answer. And the answer, as with so much in the story of interstellar objects, is stranger and more interesting than the question. Tracing an object back to its origin sounds straightforward. You have a trajectory, you have a velocity, you have the mathematics of orbital mechanics, one of the most precisely developed branches of physics, refined over centuries of astronomical observation into a set of tools capable of predicting the positions of solar system bodies decades and centuries in advance. You run the equations backward through time and you find the source. Except that interstellar space is not the solar system. In the solar system, the dominant force shaping the motion of objects is the sun's gravity. Everything else, the gravitational influence of planets, the pressure of solar radiation, the faint drag of the interplanetary medium, is a perturbation on top of that dominant force. A correction term, something that matters for precision, but does not change the fundamental picture. When you trace the orbit of a solar system comet backward through time, the sun's gravity provides a stable, well-characterized reference frame that makes the calculation reliable. In interstellar space, there is no such reference frame. The galaxy is not a simple gravitational system with one dominant mass at its center. It is a rotating disk of hundreds of billions of stars, dark matter, gas clouds, and dust, all of it moving, all of it exerting gravitational influence on everything else, none of it static enough to serve as a fixed background against which motion can be precisely measured. When an object travels through interstellar space for millions or billions of years, its trajectory is shaped by every massive object it passes near. Every star system, every gas cloud, every concentration of dark matter in the galaxy's invisible scaffolding. Reconstructing that journey from a brief observation window is like trying to reconstruct the exact path a leaf took through a turbulent river from a single photograph of where it is now. The physics is understood. The calculation is possible. But the uncertainty accumulates with every year you project backward. And by the time you are projecting millions of years into the past, the error bars on your answer have grown large enough to encompass entire regions of the galaxy. What astronomers can do with confidence is calculate 3I/Atlas's trajectory back to the edge of our solar system, to the point where the sun's gravity ceases to be the dominant force on its motion, and it re-enters the interstellar medium. At that point, they can determine its velocity relative to the local standard of rest, the average motion of stars in the sun's neighborhood, and use that velocity vector to identify roughly where in the sky it was heading from. That direction points toward a region of the galaxy in the general direction of the constellation Hercules, not a specific star, not a system that can be named with confidence and pointed to on a star map, and declared the origin of this particular piece of interstellar debris. The uncertainty in the trajectory, combined with the unknown duration of the journey, means that the number of stars consistent with three I/Atlas's incoming direction spans a volume of space containing thousands of stellar systems, any one of which could be the source, or none of which could be the source if the object was redirected by a close encounter with a massive body somewhere along its multi-million year path. But there are candidate stars, systems that align well with the trajectory, that are of the right type to produce cometary bodies of the composition 3I/Atlas appears to have, that are at distances consistent with the object's velocity and estimated age. Some of those candidates are sun-like stars, stars that formed from similar material to our own sun that would have produced planetary systems with similar chemistry to ours, that have had billions of years to develop the kind of gravitational dynamics that eventually ejects cometary material into the interstellar medium. Others are older stars, red dwarfs that have been burning steadily for far longer than our sun has existed, that formed in an earlier epoch of the galaxy's history, when the chemical environment was different in ways that might explain some of the unusual isotopic signatures in 3I/Atlas's spectroscopic data. The honest answer is that we do not yet know which star system produced 3I/Atlas. We may never know with certainty. But the attempt to find out is not merely an exercise in astronomical genealogy, a curiosity about where a particular rock came from. It is a window into the history of the galaxy in a way that no other type of observation can provide. Consider what it would mean to definitively identify the source of an interstellar object. You would have in your hands a sample of material from a specific solar system, material that formed around a specific star under specific conditions at a specific point in the galaxy's chemical evolution. You would be able to compare its composition directly to what you know about that star system from remote observation. You would be able to test, for the first time in the history of science, whether the chemistry of planet formation is truly universal, whether the same processes that built our solar system operated in the same way around another star and produced material with the same fundamental properties. You would have, in the most literal sense, a piece of another world, not a meteorite that fell from somewhere within our solar system, not a sample returned from a nearby asteroid or comet by a spacecraft mission, a fragment of a system orbiting a different star, delivered, free of charge, by the physics of orbital mechanics and the patience of geological time, directly into the detection range of our telescopes. This is what every interstellar object represents: a free sample from the galaxy's vast and otherwise inaccessible library of solar system histories. And 3I/Atlas, unlike Oumuamua, passed close enough to the sun, slowly enough relative to the detection capability of current instruments, and with enough outgassing activity to make spectroscopic analysis feasible, that the sample it represents is readable in ways that Oumuamua's brief, puzzling, silent passage never allowed. Now think about the journey itself. Whatever star system ejected 3I/Atlas did so through one of the standard mechanisms by which solar systems lose material into interstellar space. A close gravitational encounter between a comet-like body and a large planet. The same process by which Jupiter redirects comets in our own solar system, giving the smaller object enough velocity to exceed the escape velocity of its home star and continue outward indefinitely. or the gradual accumulation of gravitational perturbations over millions of years, slowly nudging an object in the outer reaches of its home system's equivalent of the Oort cloud until its orbit becomes unstable and it is released into the dark. Either way, at some point in the past, perhaps 10 million years ago, perhaps 100 million, perhaps longer, 3I/Atlas left the gravitational embrace of its home star and began its journey through interstellar space. 10 million years is a conservative estimate. 100 million years is plausible. 1 billion years is possible. Think about what 1 billion years means in terms of the journey 3I/Atlas has made. 1 billion years ago on Earth, the most complex life forms in existence were simple, multicellular organisms. Soft-bodied creatures drifting in shallow seas, leaving no bones, no shells, no fossils that most people would recognize as signs of life. The dinosaurs would not exist for another 500 million years. The mammals from which humans descended would not exist for 600 million years. The genus Homo would not appear for 997 million years. And while all of that was happening on this planet, while life was slowly, haltingly, catastrophically, and miraculously evolving from single cells to the creatures that are now watching a documentary about interstellar objects. 3I/Atlas was in the dark, moving through the cold between stars at 67 kilometers per second, passing near star systems it will never enter, drifting through gas clouds that left thin coatings of material on its surface, absorbing cosmic radiation from every direction simultaneously, with no magnetic field and no atmosphere, and no star close enough to warm it. It has been in that dark for longer than complex life has existed on Earth. And then, in the spring of 2025, it came close enough to a star, our star, for the instruments of a young technological species to detect it. That species had existed in its current anatomical form for roughly 300,000 years. It had developed radio astronomy less than a century ago. It had launched its first satellite 68 years ago. It had been systematically surveying the sky for fast-moving objects for less than 2 decades. The timing, when you examine it from this angle, is extraordinary. Not miraculous, not in any mystical sense. The timing is a consequence of mathematics and statistics. Enough objects are moving through interstellar space, and our instruments have recently become sensitive enough that detections were always going to start happening once the surveys reached sufficient coverage. We are not special for having detected 3I/Atlas. We are simply the first generation of our species with instruments good enough to notice what has always been there. But there is something worth sitting with in the image of an object that has been traveling for hundreds of millions of years through the dark, completely indifferent to whether anything was watching, and arriving precisely at the moment when something finally was. The universe has not changed. We have. We have built the instruments, developed the mathematics, trained the people, and established the survey programs that allow us to see something that would have passed completely unnoticed through our solar system for the entire prior history of our species. And now, for the third time in 8 years, we have caught something crossing our threshold. What that object has to tell us about the galaxy it has been traveling through is only beginning to come clear. And the most surprising part of what it is telling us is not about where it came from. It is about what all 3 of these visitors together imply about the galaxy we live in. Start with the mathematics. 3 interstellar objects detected in 8 years. That number sounds modest. 3 is a small number. 8 years is not a long time. And the natural instinct, when confronted with a small sample from a vast and complex system, is to be cautious, to resist drawing large conclusions from limited data, to wait for more detections before saying anything definitive about what the pattern means. That caution is scientifically appropriate. But the mathematics does not wait for caution to catch up with it, because the number 3 is not the number of interstellar objects that have passed through our solar system in the last 8 years. It is the number we detected, and those are not the same thing. The Pan-STARRS telescope that found Oumuamua was surveying a fraction of the sky at a sensitivity level that could only detect objects of a certain brightness during a window of observation that covered a small portion of each object's trajectory through the inner solar system. The same is true of the ATLAS network that found 3I/Atlas and the amateur telescope that found Borisov. These are powerful instruments by historical standards, by the standards of what will be possible in 10 years when the Vera Rubin Observatory is operating at full capacity and surveying the entire visible sky every 3 nights with sensitivity that dwarfs current systems. They are relatively limited. When you model the detection probability, when you calculate what fraction of interstellar objects passing through our solar system would actually be caught by the instruments we currently have, the number you arrive at suggests that the 3 objects we have detected represent a small fraction of the total number that have passed through during the same period. Small is an understatement. The models suggest that for every interstellar object we detect with current instruments, somewhere between dozens and hundreds pass through our solar system undetected, too small to reflect enough light, passing through at the wrong angle relative to the surveys, moving through at times when telescopes were pointed elsewhere, coming in on trajectories that kept them far enough from the inner solar system that even their closest approach was too distant for current instruments to register. If you accept the detection models, and they are well constrained enough to be taken seriously, even if not with complete certainty, then the actual rate of interstellar objects passing through our solar system is not 3 per decade. It is potentially thousands per decade, possibly tens of thousands. At any given moment, the models suggest there may be several interstellar objects inside the orbit of Neptune. Not the occasional visitor, not the rare exception, but a continuous low-level presence. A background population of objects from other solar systems, drifting through our own, passing through, departing, replaced by others coming in, from different directions. Our solar system is not sealed. It has never been sealed. It is a porous structure, its gravitational influence extending outward into interstellar space, catching some objects and accelerating others on their way, while a steady stream of material from the galaxy beyond flows through it continuously and has done so for the entire 4.5 billion years of its existence. Now scale that up. If our solar system is receiving a continuous flow of interstellar objects, material ejected from other solar systems, carrying the chemical record of their formation, drifting through the galaxy on journeys that span millions or billions of years, then every other solar system in the galaxy is receiving the same flow. 200 billion star systems, each one embedded in the same interstellar medium, each one exchanging material with all the others through the slow, continuous, gravitationally mediated process that sends cometary bodies into the dark, whenever orbital dynamics creates the right conditions. The galaxy is not a collection of isolated islands. It is a circulation system. Material formed around one star eventually finds its way to another. Chemistry produced in one solar system seeds the interstellar medium with molecules that drift to other systems. Ice that condensed around a star burning 10 billion years ago is now passing through a solar system that formed 5 billion years later, carrying inside it the molecular record of a universe that was different, younger, hotter, chemically simpler, from the one we inhabit now. This is panspermia in its broadest sense. Not the narrow version of the idea that asks whether life itself could travel between stars on the surfaces of rocks, though that question is part of this. But the recognition that matter itself travels between stars routinely, and that the chemistry of one solar system is not sealed off from the chemistry of another. The implications of this are profound, and they reach in several directions simultaneously. The first direction is purely chemical. If complex organic molecules, the building blocks of the chemistry that eventually produces life, can form in one solar system and be distributed through the interstellar medium on the surfaces of ejected cometary bodies, then the chemical environment that gave rise to life on Earth was not purely local. It was the product of a galaxy-wide chemical history. The molecules in your body are not simply the product of the sun's protoplanetary disk 4.5 billion years ago. They are the product of billions of years of stellar nucleosynthesis and chemical evolution, distributed across hundreds of billions of stars mixed together in the interstellar medium, and delivered to the locations where planets form by exactly the kind of flow that 3I/Atlas represents. You are, at the molecular level, a product of the entire galaxy, not just the solar system you were born in. The second direction the implications reach is biological. The question of whether life itself, not the building blocks of life, but actual living organisms, or at minimum the complex organic precursors that life requires, could travel between solar systems on interstellar objects is one that the detection of Oumuamua, Borisov, and 3I/Atlas has made more concrete and more urgent than it was when it was purely theoretical. For decades, the idea of panspermia, the hypothesis that life or life's precursors could be distributed through space on the surfaces of rocks, was treated as a fringe idea, interesting but unverifiable. A hypothesis without a plausible mechanism for the transport it required. The mechanism is no longer unverifiable. We have now detected 3 objects that have made interstellar journeys and passed through the inner solar system close enough to the Sun to have experienced significant heating, significant radiation exposure, and significant gravitational influence. The surfaces of these objects are real. Their interiors are protected from radiation by the outer layers in ways that models of interstellar travel have always suggested would allow certain types of organic material to survive. The journey they represent from one solar system to another is not a theoretical possibility. It is an observed phenomenon. Whether any of these objects carried anything alive is a question science cannot yet answer. The instruments required to detect biological material in the composition of a small, fast-moving object at interplanetary distances do not currently exist. But the question is no longer whether the journey is physically possible. It is now only whether the specific conditions required for survival, the right level of protection, the right internal chemistry, the right thermal history, were present in any particular case. and nobody can say with certainty that they were not. The third direction, the implications reach, is the one that connects most directly to the other mysteries your channel has explored. If the galaxy is continuously exchanging material between solar systems, if there is a constant flow of objects carrying the chemical and potentially biological history of one system into the environment of another, then the Fermi paradox looks slightly different when viewed through this lens. The silence that Fermi identified, the absence of signals, the emptiness of the sky in the face of a universe that should, by the mathematics of probability, contain intelligence at various stages of development. That silence has always been evaluated in terms of electromagnetic signals, radio waves, light, the kinds of transmission that technology produces and that our instruments are built to detect. But what if the communication happening between solar systems, if any is happening, is not electromagnetic at all? What if the only messages the galaxy actually sends between stars are physical ones, objects, matter, chemistry carried inside frozen bodies on journeys that take millions of years? What if the interstellar medium is not a void between islands, but a slow postal system, carrying packages between addresses separated by light years on timescales that make human civilizations look like brief flickers? And we have only just in the last 8 years learned to recognize what the packages look like. This is not a claim. It is a question, one that the data does not answer and that careful science does not endorse beyond the boundaries of what is currently verifiable. But it is a question that 3 interstellar objects have made unavoidable, because the galaxy is demonstrably exchanging matter, and matter carries information. And information in a universe old enough and large enough has a way of arriving at destinations its senders never anticipated, in forms its senders never designed, to be read by minds they never knew existed. 3I/Atlas is a message from the galaxy, not a designed message, not an intentional transmission, but a physical object carrying the chemical record of a solar system we have never seen, delivered to our doorstep by physics we are only beginning to understand, arriving at precisely the moment we have just barely learned to recognize it for what it is trying to tell us, what the pattern of 3 visitors in 8 years is trying to tell us, is that the universe is not empty between the stars. It is full, full of material, full of chemistry, full of the slow exchange of matter between solar systems that has been happening since the first stars formed and will continue happening until the last ones go dark. We are not alone in our solar system. We have never been alone in our solar system. We just needed the right instruments to see what had always been there. Every time a new interstellar object is detected, the same question surfaces. Not immediately. Not in the first press releases or the initial scientific papers, which are careful and measured and appropriately focused on what the data actually shows. But underneath all of that, in the conversations that happen after the conferences, in the papers that get submitted and sometimes rejected and sometimes published in journals, that other scientists read carefully while maintaining a studied expression of professional neutrality. The question is always there. Is it natural? This is not a question that gets asked about every unusual astronomical object. When a pulsar is discovered with a slightly different period than expected, nobody asks whether it might be artificial. When a galaxy shows an unusual morphology, nobody suggests that intelligence might be responsible. The universe is full of strange things, And science has learned through centuries of experience that the default assumption when something strange is observed is that a natural process we do not yet fully understand is responsible, not that an intelligence we have never detected has intervened. That default assumption is good science. It is also, in the specific case of interstellar objects, more complicated to apply than it initially appears, because the question of whether something is natural depends entirely on knowing what natural looks like. And for objects that have spent millions or billions of years in interstellar space, formed around a star we cannot observe, produced by processes that operated under conditions we have not directly studied, natural is not a well-defined category. We know what natural looks like for solar system bodies. We have 4.5 billion years of examples, thousands of cataloged objects, and a well-developed theoretical framework for understanding how comets and asteroids and Kuiper belt objects form and evolve. We have 3 interstellar objects, 3 data points from which to construct a picture of what natural looks like for material that has made the journey between stars. Oumuamua showed us that natural in the interstellar context might include things we have no framework for. Its shape, its acceleration, its complete absence of outgassing. None of these fit neatly into any known category of natural solar system object. The explanations that were offered, molecular hydrogen ice, nitrogen ice slabs, fractal dust aggregates, were all physically possible and all required assuming conditions that had never been directly observed and could not be verified from the data available. Borisov showed us that natural in the interstellar context can also look completely familiar. A comet is a comet, whether it formed around our sun or a star 100 light years away. The chemistry of planet formation is reproducible. The physics of cometary outgassing is universal. Borisov behaved exactly as a natural comet should behave, and nothing in its data required any explanation beyond the standard framework of cometary science applied to an object that happened to have formed elsewhere. 3, I/Atlas sits between them. Its coma and outgassing behavior are cometary, natural, familiar, explicable within the existing framework. Its chemical signature shows the fingerprints of a different formation environment. Specific, interesting, but not inexplicable through natural processes. Its trajectory is hyperbolic, the result of physics that is completely understood and that requires no special pleading. In all of these respects, 3I/Atlas is consistent with being a natural object. But consistent with being natural is not the same as proven to be natural. And the history of science is full of cases where the distinction between those two things mattered enormously. Abraham Loeb has made this argument more publicly and more persistently than almost anyone else in mainstream astronomy. Loeb is not a fringe scientist. He is the former chair of the astronomy department at Harvard University, the founding director of the Black Hole Initiative, and one of the most cited astrophysicists of his generation. When he published a paper in 2018 suggesting that Oumuamua's properties were consistent with an artificial light sail, the response from the scientific community was largely dismissive, not because the physics of his argument was wrong, but because invoking artificial origin violated the scientific norm of preferring natural explanations when they are available. Loeb's counterargument was simple and has never been fully answered. The norm of preferring natural explanations is valid when natural explanations are available. When every proposed natural explanation requires invoking conditions that have never been observed, processes that have never been measured, and physical states that exist only in theoretical models, The question of whether an artificial explanation deserves consideration alongside them is not obviously answered by appealing to the norm. For 3 I/Atlas, the situation is different from Oumuamua. The natural explanations are more readily available. The cometary behavior provides a familiar framework. The case for invoking artificial origin is considerably weaker than it was for Oumuamua, where the data actively resisted natural explanation at multiple points simultaneously. But the question itself, the underlying question that Oumuamua made unavoidable and that every subsequent interstellar detection keeps alive, is not answered by the relative naturalness of any particular object. The question is whether, in the continuous flow of material that the galaxy exchanges between solar systems, any of it could be artificial. Not this specific object. Not 3 I/Atlas or Oumuamua or Borisov in particular, but somewhere in the vast, uncatalogued population of interstellar objects drifting through the galaxy, somewhere among the thousands or millions of objects that our instruments are not yet sensitive enough to detect. Could any of it be the product of a technology rather than a geology? The mathematics of this question is uncomfortable to sit with. If technological civilizations exist or have existed in the galaxy, and the combination of the Drake equation, the age of the universe, and the abundance of potentially habitable planets makes a purely empty galaxy increasingly difficult to defend statistically, then some of them may have been producing technology for far longer than our own civilization has existed. Civilizations that have had not centuries, but millions of years to develop their capabilities. Civilizations that may have sent probes into interstellar space, not faster than light, not through wormholes, but simply on the slow, patient trajectories that physics allows, launched long enough ago that they have had time to cross the light years between stars on purely ballistic paths. A probe, launched 100 million years ago by a civilization that no longer exists, would be, by now, drifting through the interstellar medium indistinguishable in its basic orbital properties from a naturally ejected cometary body. It would be cold. It would be dark. It would be coated in the same radiation-processed organic material that accumulates on any surface exposed to cosmic rays for geological timescales. It would not be transmitting. Any power source capable of maintaining a transmission for 100 million years is beyond anything our current physics can conceive. It would look from a distance like a rock. This is not a claim that any interstellar object we have detected is such a probe. It is a recognition that the detection of a probe, if one existed and passed through our solar system, would be extraordinarily difficult to distinguish from the detection of a natural object, unless we were able to get close enough to examine it in detail, and with instruments sensitive enough to detect the signatures of manufactured structure beneath the accumulated coating of interstellar processing. We have not been able to do that with any of the 3 objects we have detected. Oumuamua was gone before we gathered enough data. Borisov was studied more extensively, but showed nothing that required a non-natural explanation. 3 I/Atlas is currently our best opportunity, passing through the inner solar system close enough and slowly enough that the generation of telescopes and space observatories we currently possess could, in principle, gather more data than we have ever gathered on any interstellar object. Whether that data will resolve the question is uncertain. What is certain is that the question deserves to be asked seriously, not sensationally, not with the assumption that every unusual object is artificial or that science is on the verge of confirming extraterrestrial contact. But seriously, in the way that any scientifically legitimate possibility deserves to be examined when the data does not conclusively exclude it. The universe has had 13.8 billion years to produce intelligence. Some of what it produced may have sent things into the dark. Some of those things may be passing through our solar system right now. We have the instruments for the first time in our history to notice. Whether we have the will to look carefully enough, and open-mindedly enough, and rigorously enough that whatever the answer turns out to be, we can be confident we found it honestly, is a different question. One that each new interstellar detection makes more pressing, and one that the next generation of instruments, arriving within the next decade, will force us to confront with a seriousness and a specificity that our current tools do not quite allow. We are at the beginning of something, not the beginning of interstellar objects entering our solar system, that has been happening for 4.5 billion years, continuously, without interruption, regardless of whether anything on the third planet from the sun was capable of noticing. The objects have always been here. The exchange has always been happening. The galaxy has been circulating its material through our solar system since before the Earth had finished forming. We are at the beginning of our awareness of it. And awareness, in science, is not a passive state. It is the precondition for everything that follows. For measurement, for understanding, for the kind of accumulated knowledge that eventually produces insight. The moment when enough data has been gathered and enough patterns have been recognized that the picture changes from a collection of isolated observations into something coherent, something that tells a story. 3 interstellar objects in 8 years is not yet that story. It is the first sentences of it. The Vera Rubin Observatory is the instrument that will write the rest. Construction on the Vera Rubin Observatory in Chile, named for the astronomer whose work provided some of the first compelling evidence for the existence of dark matter, was completed in the mid-2020s. Its primary mirror is 8.4 meters across. Its camera is the largest digital camera ever built for astronomy, capable of capturing a field of view roughly 40 times the area of the full moon in a single exposure. And its survey strategy, the Legacy Survey of Space and Time, which will systematically photograph the entire visible southern sky every 3 nights for 10 consecutive years, is designed to detect moving objects with a sensitivity and completeness that no previous sky survey has come close to achieving. For interstellar object detection, the implications of the Vera Rubin Observatory are transformative. Recall the detection, probability calculations. The models that suggest for every interstellar object we currently detect, dozens or hundreds pass through our solar system unnoticed. Those models are calibrated to the sensitivity of current instruments, Pan-STARRS, Atlas, and their contemporaries. The Vera Rubin Observatory is not a modest improvement on those instruments. It is an order of magnitude increase in sensitivity, combined with an order of magnitude increase in sky coverage frequency. Scientists estimate that Rubin will detect a new interstellar object approximately once per year. Some estimates are more optimistic than that. Once per year means that within a decade of full operations, we will have a catalog of interstellar objects numbering in the dozens, not 3 data points from which to extrapolate cautiously. Dozens of objects, each one with its own trajectory, its own composition, its own physical characteristics, its own story of origin and journey and arrival. A genuine dataset from which patterns can be extracted not tentatively, but with the statistical confidence that science requires before it is willing to say something definitive. That dataset will answer questions that three data points cannot touch. It will tell us whether the population of interstellar objects is dominated by comet-like bodies like Borisov, or whether objects like Oumuamua, strange, dry, enigmatically accelerating, are common. It will tell us whether the chemical diversity of interstellar objects reflects the chemical diversity of stellar populations across the galaxy, or whether the composition of interstellar objects is more uniform than their origins would suggest. It will tell us whether certain regions of the galaxy produce more interstellar objects than others, and what that implies about the environments in which planetary systems form and evolve. And it will do something that no amount of theoretical modeling can substitute for. It will give us objects we can prepare for. One of the most frustrating aspects of all three interstellar detections so far is that they were found too late. Oumuamua was already past perihelion, already beginning its outbound journey, by the time anyone noticed it. The window for detailed study was weeks, not months. Borisov gave more warning but was still a fast-moving target that required rapid reorientation of observing resources. 3I/Atlas, detected by a survey specifically designed for early warning, has provided more lead time than its predecessors, but still not the lead time that would allow a spacecraft mission to be planned and launched before the object departs. Rubin will change this. By detecting interstellar objects earlier in their approach, potentially months or years before they reach the inner solar system, Rubin will provide the planning time that mission designers need. And mission designers are already planning. The concept that has attracted the most serious attention is called the Comet Interceptor mission, a European Space Agency project that is already in development, designed to sit at a gravitational equilibrium point between the Earth and the Sun and wait. Not for a specific target, because no specific target is known at the time of launch, but for whatever Rubin finds that fits the criteria for a scientifically valuable close encounter. When a suitable object is identified far enough in advance, the comet interceptor will be redirected, using the velocity it has already accumulated by sitting at the equilibrium point, to intercept the target and fly through its coma, gathering in situ data that no telescope observation from Earth can match. The data that a flyby mission could gather from an interstellar object is qualitatively different from anything we can obtain remotely. Not spectroscopic averages of the light reflected from a nucleus too small to resolve. Not brightness measurements that tell you about size and rotation rate, but nothing about internal structure. Actual samples of the gas and dust in the coma. Direct measurements of the magnetic field environment around the nucleus. Images at a resolution that reveals surface features, craters, ridges, compositional variations, the physical record of a journey through interstellar space written into the geology of the object itself. If that object turned out to have unusual properties, if it showed the kind of anomalies that would push the boundaries of natural explanation in the way that Oumuamua once did, those measurements would provide the data needed to evaluate those anomalies seriously. Not from a distance, with instruments that cannot resolve the nucleus, but up close with the full suite of sensors that an in situ mission carries. There is also a more ambitious proposal, a concept that exists at the edge of current technology and that has been studied seriously enough to have acquired a name and a community of researchers working on its feasibility. It is called Project Lyra. The question Project Lyra asks is the one that every physicist who has spent time thinking about interstellar objects eventually arrives at. Could we catch one, not intercept it, fly through its coma, and continue onward? Catch it, match its velocity, enter its gravitational environment, observe it at close range for months or years rather than hours. The mathematics of catching an interstellar object are brutal. These objects move through our solar system at speeds that dwarf the velocities of any spacecraft ever launched. The gap between how fast they move and how fast we can currently accelerate a spacecraft is not a small engineering challenge. It is a fundamental constraint of the energy available to chemical and even current ion propulsion systems. But the mathematics are not absolutely prohibitive. A spacecraft launched on a highly optimized trajectory using the sun's gravity to accelerate in a close solar flyby in the way. That certain gravitational assist maneuvers work, but taken to an extreme that current missions have not attempted, could, in principle, reach the velocities needed to pursue an interstellar object if that object were detected early enough and if the launch window were exploited with sufficient urgency. The key word is early enough, which is, again, where Rubin comes in. Earlier detection means longer lead time. Longer lead time means more options for trajectory design. More options for trajectory design means that the window of feasibility for a rendezvous mission, currently extremely narrow, requiring a level of response speed that no space agency has ever operated at, begins to widen. We are not there yet, but we are closer than we have ever been, and the direction of travel is clear. Within a decade, we will be detecting interstellar objects routinely. Within 2 decades, we may have flown a spacecraft through the coma of one. Within 3 or 4 decades, if the political will and the scientific funding exist, we may have launched a mission designed to catch one. The object that mission catches may tell us more about the galaxy in a single close encounter than all the remote observations of all the interstellar objects we will detect from Earth in the same period combined. It may answer the question of whether Oumuamua was simply an unusually shaped rock with unusual surface properties and an unusually efficient reflective area. A natural object that happened to combine several unusual characteristics in a way that confused our instruments and frustrated our explanatory frameworks. Or it may not answer that question cleanly. It may arrive at close range and find something that raises the question more sharply than ever. Surface features that do not correspond to natural geological processes, structural regularities that natural formation cannot easily produce, chemical signatures that point not to a formation environment around a distant star, but to something that requires a different kind of explanation entirely. We do not know. That is the honest answer to every question the 3 interstellar objects we have detected have raised. We do not know what Oumuamua was. We do not know precisely where 3I/Atlas came from or how long it has been traveling. We do not know what fraction of the continuous flow of interstellar objects passing through our solar system consists of objects like Borisov, objects like Oumuamua, and objects unlike either of them in ways we have not yet had the opportunity to characterize. But we are about to start finding out. The instruments are coming. The missions are being designed. The survey that will transform our detection rate from 3 objects per decade to potentially dozens per year is already operating and gathering data. We are at the hinge point, the moment just before the story accelerates. The last few years of working with a handful of data points before the dataset opens up and the patterns become visible, and the questions that have been sitting unanswered since October 2017 finally have enough material to work with. 3 I/Atlas is not the end of the interstellar object story. It is not even the middle. It is the third paragraph of the first chapter of something that will occupy astronomers for decades and that may eventually produce answers that change not just our understanding of the galaxy, but our understanding of what the galaxy contains and what it has always contained, and what has been flowing through the space between stars since long before we existed to wonder about it. The visitors will keep coming. We will keep getting better at seeing them. And what we find when we look more closely, with better instruments from shorter distances, with the full analytical power of a scientific community that is finally taking this seriously, may turn out to be the most important thing our species has ever discovered. Or it may turn out to be rocks. Beautiful, ancient, chemically fascinating rocks that have crossed the light years between stars and arrived in our solar system carrying the chemical record of worlds we will never visit. Either answer would be extraordinary. Either answer would change everything. If this changed the way you see the space between the stars and the objects that move through it, the cosmic depth has more waiting for you. Subscribe, and I will see you in the next one.